So as I'm recording this in September 2025, there's been a lot of discussion about the Western disturbances contributing to the very heavy rain we've been experiencing in northwestern India, in the Himalayan foothills, northern Western Ghats from Mumbai into Gujarat, Mumbai meaning Maharashtra into Gujarat, Punjab, Rajasthan, Pakistan, of course, and from Uttarakhand into Jammu and Kashmir in the Himalayan foothills. And Western disturbances are well-known features that mostly occur in the winter. And there's been a long discussion about whether there is a trend in them, and the results seem, not so robust. But they occur because of certain phenomenon, typically in the Mediterranean, then they truck along into the Western Indian Ocean, Himalayas, and so on. And there are processes that are involved in generating this. So this nice paper that appeared last year in 2024 discusses many of these issues: increasing frequency and lengthening season of Western disturbances that are linked to increasing strength and delayed northward migration of the subtropical jet. Okay, what does it mean? Let's read the abstract and look at a few figures, and then we'll look at some key points. It's a nice long paper, and I'm not going to read all of it, obviously. Western disturbances are cyclonic storms that travel along the subtropical jet, bringing the majority of seasonal and extreme precipitation to the Hindu Kush, Karakoram, and Western Himalaya in the winter months, boreal winter. They are a vital component of the region's water security, although typically most common in the winter. WDs, Western disturbances, can also interact with the summer monsoon, leading to catastrophic consequences, as we've been seeing this season. These seem to be happening more frequently, and along with increasingly harsh winter seasons, questions are now being asked about how climate change is affecting WD frequency and intensity in both summer and winter seasons. An analysis of 17 previous studies assessing trends in WD frequency revealed no consensus, at least in part because they quantified trends in different regions, seasons, and time periods, so they're not apple-to-apple comparisons. In this study, a more robust approach is used, quantifying trends in WD frequency and intensity by region and month, using a track catalog derived from 70 years of European Center for Medium Range Weather Forecast, ECMWF reanalysis era 5 data. Winter WDs have increased significantly over the western and central Himalaya and the Hindu Kush in the last 70 years. This trend is attributed to a strengthening of the subtropical jet. The WD season has also significantly lengthened, with the WDs becoming far more common in May, June, July months, where they were previously rare. For example, WDs have been twice as common in June in the last 20 years than during the previous 50 years. This is attributed to a delayed northward retreat of the subtropical jet, which historically has occurred before the onset of the summer monsoon. The most important implication is that the frequency of monsoonal WDs is increasing significantly, and therefore, due to climate change, catastrophic events like the 2013 Uttarakhand floods and the 2023 North India floods are becoming much more frequent. But again, this statement jumps a little ahead, because if the WDs have increased in June, are the floods also in June? Well, this year most of the floods have occurred in July and August, and now we are in September. So we'll see that you can't keep quibbling about little things, and yet it matters, because are the processes the same of the WDs in the summer? Are they occurring at the same place in the far west, or are they occurring closer to the Himalayas, and so on? So those are questions that still need to be looked at. In other words, is every cyclonic system coming into the Indian subcontinent a western disturbance, or is there another process that can generate the western disturbance like cyclonic features that can interact with the basic monsoonal circulation to create heavy rain events, or are they even contributing to the heavy rain events? If they are not bringing enough moisture, how do they increase the rainfall? Because there are other things happening over the Arabian Sea. The winds are shifting north because of the Middle East warming, and those northward shift of the winds are pumping more moisture into northwest India, Pakistan, and the Himalayan foothills. So what is the real reason? So these are always interesting questions that will be investigated along the way. And then there are also decadal variabilities, and if one reanalysis product says something, is that really true, and so on. Okay, there is some background material. Western disturbances are the upper level troughs embedded in the subtropical westerly jet. So the westerly jet comes south during fall, winter, spring months as the cross-equatorial flow for the summer monsoon begins. It begins to get pushed northward, and the idea is that maybe its northward migration has changed in seasonality, delayed with northward movement. Dynamical instabilities in the jet often rising over the Mediterranean grow baroclinically as they move eastward, arriving as cyclonic winter storms over the Hindu Kush, Karakoram, and Western Himalaya several days later. A lot has been discussed on these. On average, 6 to 7 strong WDs pass over the Indian subcontinent each month during winter. 6 to 7 each month. Here they are responsible for the majority of winter mean and extreme precipitation. WDs affect Iran, Afghanistan, Pakistan, and India, and occasionally extend their reach further east to Nepal and Bangladesh. If you remember the Himalayan topography, it's way to the north and west in the western part, and dips down into southern parts, and as it comes east towards Bangladesh, Nepal, Bhutan, and Burma, and so on. Right? So on average, 6 to 7, as we said. However, their impact is most strongly felt over North India and Western Himalaya, as where they cause cold waves, avalanches, landslides, lightning, and heavy precipitation through interactions with the orography. The aim of this paper, I'm jumping ahead, is to resolve these disagreements using a more robust analysis method relying on a database of WD tracks covering 1950 to the present day, 70 years. We split the problem into 4 research questions. Do trends in WD frequency vary spatially? Do trends in WD frequency vary seasonally? If so, are WDs increasing in frequency in the pre-monsoon and monsoon seasons, extending their range beyond the winter months as hypothesized by Valdia in 2020? Can differences in trends be explained by different definitions of WDs, namely using different intensity thresholds? What are the causes of robust trends in WD frequency? Okay, so here is the quick look at all the studies that looked at WD activity, and you can see various periods are covered looking at frequency here, and this is various other frequencies still here, GPH variability in meters, so geopotential height, wave power, and GPH, regime days. So various things are looked at. They are not apple to apple, different periods, different quantities, etc. And they are different papers, as you can see. So basically no robust signal when you compare the previously published studies. Jumping ahead, the seasonal cycle of WDs computed between 1950 and 2022. You can see here WD intensity percentiles from 0 to 100. You can see January, February, March, so December, January, February, March, maybe even starting in November. So you can see that there is a summer lull. It drops off in May and then drops more seriously into June, July, August, and begins to pick up in September, October, November, and into December. So December to March, we are looking here at various factors, verticity, etc. Map of the average WD frequency from December to March, computed as the number of unique WD tracks that enter a given 2.5 degree by 2.5 degree grid per month. The main location of the subtropical jet is plotted in blue, computed for each longitude as the latitude during that season that has the highest mean 200 hectopascal zonal wind speed, which is the jet. C is same as B, but for April to June. So frequency, so you can see here track density in WDs per grid box, 2.5 degree by 2.5 degree, and there is the jet, so you can see directly the relation between the jet. And in April to June, the jet moves northward, clearly you can see, with the arrival of the pre-monsoon winds into monsoon. So you are not looking at July, August here, so that remember that, because December to March, April to June. Is this year in 2025 special that did we have more western disturbances in July, August compared to this paper, for example? Well, that's still out there. Okay, so part of the problem is that they do analysis about this subtropical jet, and they decide that doing annual trends is not very useful because the western disturbances respond to changes in subtropical jet in different ways depending on the season, because the background winds, the temperature gradients, equator to pole temperature gradients, energy, everything is different. Winter season has very strong equator to pole temperature gradient, strong subtropical jet, and so on, and the positions are much further south, etc. The most obvious example is the relationship between the jet latitude and WD frequency. During the summer season, when the jet is far north, we would expect a negative correlation between jet latitude and WD frequency, as anomalous southward excursions of the jet are more likely to bring WDs to North India. Conversely, in winter months, anomalous southward excursions of the jet move it away from the baroclinic environment of the Himalayas, reducing WD frequency and intensity. If you don't know what baroclinic is, basically you can think of it as vertical shear in the jet, which, if it reaches a critical threshold, the shear then releases energy into cyclonic systems, which can then get advected, let's say, by the jet itself. And of course, when you run into the Himalayas, you are going to create these kind of vertical shear in the jet as well. So baroclinic, in an approximate sense, is vertical shear. There are many details. I'm being very brief. So jumping ahead on the main analysis. In summary, WD frequency has significantly increased over the last 70 years in January and in April through July. So here July is mentioned, but April, May, June. In January and April, we attribute this to increasing jet strength. In June and July, we attribute this to decreasing jet latitude. In other words, the jet is more likely to remain over the northern India and Pakistan as the monsoon develops, rather than receding northwards as it typically did in the second half of the 20th century. My guess is that these winds, the low-level jet over the Arabian Sea that is getting pulled more and more northward at the northern edge, is sending some moisture and winds to run into these jet winds and creating some cyclonic systems. So this paper doesn't necessarily look at where they are being born in April, May, June, July, right? So are they same as the winter genesis region? These have to be considered as well. Trends in WD frequency from 1950 to 2022, number of unique tracks passing through each 2.5 degree by 2.5 degree grid box per month as before, and aggregated by season, and the trend is computed. So here we are looking at track density, WDs per grid per month per century. Nonetheless, just look at the colors, so you can see there are some negative frequencies, so reduced, and positive frequencies. So these are all WDs. The strongest of the WDs concentrate here over northwestern India, where we are having more and more extreme rainfall in the recent decades, which has been attributed to rapid warming that's happening over the Western Asian Mediterranean region, and the low level the jet getting pulled northward during the monsoon season. And in April to June you can see that there is some increase in frequency with decrease on either side, but this decrease, obviously Western disturbances are here. When you say decrease here, it's generally related to the metric you use in terms of vorticity and so on. Okay, so this is for all WDs and this is for strong WDs. So strong WDs here actually have negative numbers in April to June, but all WDs show a positive trend. So what does this all mean? You have to still be careful about concluding much from this. To determine whether trends are sensitive to WD detection thresholds, trends for strong WDs, i.e. those whose peak 350 hectopascal vorticity is in the top half of the population, are given in B and D. B and D, and here, and so these are strong. I don't know, I'm getting confused, but nonetheless the main point is that there is seasonal change, intensity change, frequency change, but here strong ones seem to have decreased when you look at April to June, whereas all WDs have increased. And as I said, the details of the genesis process, whether they are same in winter as opposed to April to June, it's not so obvious. December to March here, trends in 200 hectopascal seasonal mean zonal wind from 1950 to 2022. So jet axis 1950 to 1970 in the blue. So you can see the probability distribution function of sorts, and 2000 to 2020. Do you see a statistically significant difference? Well, of course, the argument that it is significant. Trends in 200 hectopascal seasonal mean zonal wind from 1950 to 2022, December to March and April to June. Splitting indicates where trends have significance of more than 95%. Histogram on the right of each subplot show the latitudinal distribution of the jet axis for the respective season. So it's not PDF, just the distribution computed as the latitude at which the monthly mean 200 hectopascal zonal wind reaches its peak when averaged across 50 to 80 degree east, which is the Indian longitudes. Okay, so what do you see? Basically, there have been some changes. Does this prove that the process or the mechanism proposed here is able to explain the so-called westerly disturbances? Are they really Western disturbances or just meeting some vorticity criteria? Are they being born in the far west? For example, here December to March, you have negative zonal wind speed trend. Here is negative and positive here, negative and positive here in April and June as well. So southward shift obviously means weaker winds here, northward shift means stronger winds here, and so on and so forth. So take it for what it is. Trends in selected WD and subtropical jet monthly statistics. I won't go into details, but basically your mean jet core latitude, you can see in terms of degrees. Do you see a change? It's clearly higher frequencies here at 28 degrees latitude for mostly the winter months, and going northward during the fall spring months, as you can expect with the seasonality we already saw. This is the mean jet core strength in let me read the caption carefully. Trends in, I read it, I think I remember it, and then I begin to forget the details. Trend in selected WD and subtropical jet monthly statistics. Jet statistics are computed as an average between 20 to 40 north and 50 to 80 degree east. At the end of each row, plus sign indicates a positive trend, a negative sign. So you can see here positives and negatives. Negatives on the northern and southern end of the jet, and positive trends here. Okay, and similarly here positive trends and weak positive and strong negative here. Okay. these are colored black and gray respectively for significance level of greater than 95% or less than 0.5 p of 0.5. Latitude of the jet core, sorry, 0.05 is 99 percentile, 95 here, so it's much more significant than I mentioned before. Latitude of the jet core measured as the latitude where the zonal average of 200 hectopascal U is maximum at that time. Strength of the jet core is taken as the maximum of the zonal average of 200 hectopascal wind, i.e. the zonal wind speed at the mean core location. The number of, so those are the numbers: mean jet core latitude, mean core jet strength in meter per second. Do you see any change? Well, you decide. WD frequency per month. Now you begin to see some color changes over here in the last, let's say, 40 to 50 years. And of course, mean WD intensity. Do you see any significant change? Well, here you are. So looking at seasonality here, this is the basically insignificant region. Correlation coefficients here for WD frequency, jet strength, relation between them, WD frequency and jet latitude, WD intensity and jet strength, WD intensity and jet latitude, and jet latitude and jet strength. What does it tell you? Clearly, is there a trend or is there multi-decadal variability? How are each one of them related to each other, right? So it's not as straightforward as one would imagine. Let's read conclusions and the main points. Western disturbances are synoptic scale cyclonic circulations. There are, typically natural variability of December to March as the main season in terms of the maximum frequency and intensity. Given this, it's important to quantify trends in WD frequency and intensity so that adequate preparations, so they are causing extreme events, so obviously you want to see how they are changing, especially if they are also intruding into the monsoon season. However, previous studies have largely disagreed on the sign and significance of WD frequency trends. In this study, we look for a more robust approach, breaking down the trends both spatially and seasonally using 70 years of reanalysis data, but only one reanalysis. The key results are as follows. As previously found in Hunt et al. 2018a, WDs as measured by their 350 hectopascal relative vorticity are much stronger in winter months still. WDs whose peak intensity exceeds the 75th percentile virtually never occur between June and September. WD track density varies considerably between the winter and pre-monsoon months, here taken as April to June. During winter, tracks predominantly impact the Hindu Kush and Western Himalaya and can often persist long enough to reach the central and eastern Himalaya. During the pre-monsoon months, track density is more spread, with many more impacting Karakoram and relatively few impacting central or eastern Himalaya. So track, intensity, number, everything is different, frequency. WDs have increased significantly over the Western Himalaya and Hindu Kush in winter, and significantly over these regions and the Karakoram in the pre-monsoon months and early monsoon. As these approximately follow mean track density, there has been no marked shift in seasonal track density, nor do any regions show a significant decline in WD frequency. So kind of complicated when you look at everything, but it doesn't matter. Upper level zonal winds wind has increased significantly over North India and Pakistan in both winter and pre-monsoon, which implies subtropical jet has increased in intensity in winter and is more frequently situated over the region during pre-monsoon and early monsoon. Over the box, incorporating the most of their population, so 20 to 40 north, 50 to 80 east, WDs have significantly increased in frequency in January, April, May, June, and July. Increases in May and June over the last 20 years have been particularly notable. For example, WDs in June are now twice as frequent as they were for much of the 20th century. Remember, here there is already a discussion of the definition of WDs, thresholds, but still there is nothing like genesis region that's considered. Are they being born much more closer to Western Himalaya and over Pakistan and so on. That question will still depend on whether the mechanisms are still the same throughout the year. So that's the critical question in my mind. We attributed the January and April frequency increases to a strengthening of the subtropical jet, and the June and July increases to a delayed northward retreat of the jet. So these are much more local. So if we look at the jet axis, you can see these parts are not very different. It's here that the differences happen. So it's much more southward in the winter month than in the pre-monsoon monsoon months. So where is the genesis happening in the increased frequency during the pre-monsoon monsoon months? That's not very well answered here, right? Key results as previously found in Hunt et al. We said 350 hectopascal relative verticity are much stronger in winter months. WD track intensity varies considerably between winter and pre-monsoon months, taken here as April to June. During winter, tracks predominantly impact Hindu Kush and Western Himalaya and can often persist long enough to reach central and Eastern Himalaya. During pre-monsoon months, track density is more spread. I think I already read this, but nonetheless. WDs have increased significantly over the Western Himalaya and Hindu Kush in winter, and over the same regions and Karakoram in the pre-monsoon months and early monsoon months. There has been no marked shift in seasonal track density, nor do any regions show significant decline in WD frequency. I was already here, so I went back and got stuck there. But nonetheless, January, April, trends in WD intensity. Trends in WD intensity are statistically significant only in April and May, where they have declined slightly. We were not able to link these to changes in the jet behavior, so they remain an open question. And my question would be whether that is related to the wind shifts over the Arabian Sea in the pre-monsoon months as well, which have been argued to increase the heat waves over northwestern India as well in the pre-monsoon season. Okay, so this changing seasonality of WD frequency does not wholly explain the disagreement between earlier studies in establishing the sign and significance of historical WD frequency trends. So many questions still remain. I won't go into the detail here. There has been no significant spatial shift in WD track density in the last 70 years, and so it's unlikely that the cause of previous disagreement is related to the track shifts and so on. But nonetheless, some open questions remain. One possible resolution which has not been explored here is the role of interdecadal variability, which I mentioned in this figure here. So where is the trend? Is it just up and down in terms of this is seasonality, of course, but what if you have mostly winter being stronger in some decades and summer, winter is here, and spring and summer picking up duration and frequency in some other latitudes, right? WD track density varies considerably between winter and pre-monsoon months. During the winter, tracks predominantly impact Hindu Kush, Western Himalaya, and often persist. So we are repeating this again because I got stuck here. I'm getting old, folks. Okay. So they didn't consider decadal variability. This is tricky because multi-decadal variability could be a 30-year time period and global warming may make it 50 years. So multi-decadal variability may still remain, but its periodicity may change, may get shorter or longer. So it's always tricky to separate secular trends and decadal variabilities and so on. Aside from this, an important shortcoming, of course, is that they use only one reanalysis. So worth noting that the results presented here are somewhat at odds with those previously presented by the same author, in which a similar method was applied to coupled model intercomparison project 5 CMIP 5 models, which indicated a significant decline in WD frequency and intensity, which was attributed to weakening baroclinicity. So obviously more thorough review using the CMIP 6 model output is required, but is there a big difference between CMIP 5 and CMIP 6? Not really. So this reanalysis is generally considered as data. We always call it reanalysis data, but they are a blend of models and data, and they still have a lot of issues, but nonetheless that's the best we can have in terms of dynamically interpolated products, historical products that can be used for analysis like these, which are useful, but we need much more understanding of the basic processes to understand the trends. Okay, let's leave it here.